Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Paul Beckman, who is a postdoctoral fellow at UT Austin. Paul will be speaking on fast transforms for Gaussian random fields. Take it away, Paul.
Great. Yeah, thanks for the introduction and thanks for the opportunity to give a talk. Um, so the focus of this talk will be on developing two particular fast transforms, which can be used for harmonic analysis in sort of a wide range of applications. But my background is mostly in spatial statistics, so we'll use Gaussian random fields or Gaussian processes as our sort of motivating example for these methodological developments. And then at the end of the talk, I'll mention some other applications outside of statistics where we can use these tools. So let me advance this slide if I can. Beautiful. Okay, so just to lay the groundwork for the sort of mathematical object that we're interested in, we'll be thinking about Gaussian random fields, which are stochastic processes Y, which are indexed by this location X, for which the joint distributions of observations of our process at any finite set of locations, say x1 to xn, that joint distribution is Gaussian. So this distribution is fully specified by this covariance function k theta that we show here, which essentially tells us how observations of our process at a point xj and at a point xk depend on each other. What does the correlation structure or the covariance structure look like? And we'll assume, without loss of generality, that this is a mean zero process. So we're considering only the fluctuations and trying to capture that structure. Um, so generally, with this type of statistical model, we want to do things like sample from our process or predict the value of y of x for some new unobserved location x. Or do things like parameter estimation to estimate these parameters theta by, for example, minimizing this negative log likelihood or performing maximum likelihood estimation. And you see that this involves linear algebraic tasks like solving linear systems, computing log determinants, things like this. So this covariance matrix and this covariance function k theta are really the central players in this setup. So Gaussian random fields are sort of applicable on a wide variety of domains, which is part of the reason for their popularity. So you can have something like discrete time series for, say, a medical device measuring at regular intervals. So now your x's are indexed by the integers. You could have, say, continuous time seismic data at a single location. So this is now indexed by the real numbers. You could have something like air quality measurements taken at stations across a city. So now you're indexed by essentially the plane, two-dimensional Euclidean space. You could have geophysical data like sea surface temperature measured across the surface of the Earth. So now you want a statistical model that lives on the surface of the sphere. Or you could have something like perturbations in electrical potential measured on the surface of some manufactured device. So you want now a statistical model that represents uncertain quantities on the surface of some manifold, right? So and across all of these sort of domains, Gaussian random fields are also popular because they provide not only predictions of the value of your observable at unobserved locations, so we can compute y of x for new x's where we didn't actually observe the data, but these predictions also come with uncertainties, right? They come with these covariances, so we have uncertainties or error bars that incorporate all of the sort of correlation information in our data to tell us how certain we should be about these predictions. So the modeling paradigm that we're interested in and that I'll talk about today is modeling in the spectral domain. So what's sort of standard practice when you're using a Gaussian process model is to pick a parametric family of positive definite closed form covariance functions, k theta. So here we have the Gaussian, and on the right we have the Matern covariance, where this script k is a Bessel function of the second kind, and this parameter nu changes how smooth our process is. So if nu is small, then it's non-differentiable. If you increase nu, you get once, twice, three times differentiable processes, right? So these sort of closed form models are handy because you can just evaluate entries of your covariance matrix. But because positive definite functions are in general difficult to derive in closed form, only a handful like these are used in practice. And these standard covariance functions may not actually capture the scientifically relevant phenomena in your particular application data, right? You may want a more flexible model class than that's afforded by these. So if we make the following assumption that k theta is also stationary, meaning that it depends only on x minus x prime, this distance we'll call r, instead of both arguments separately, then Bachner's theorem tells us that there exists a spectral density S theta, which is exactly the Fourier transform of our kernel, right? And numerically, we could compute our covariance function k theta from the spectral density S theta by using some quadrature rule, right? So we're approximating this Fourier integral using a quadrature rule with nodes omega k and weights gamma k, right? So this is extremely appealing from a modeling perspective because it allows practitioners to write expressive statistical models that capture the relevant phenomena, right? Because it's much easier to specify a non-negative function s theta than it is to specify a function which you have to guarantee is positive definite, like the covariance function k theta, right? So it leads to much more flexible models, but it presents a sort of computational challenge, which is that we now need fast transforms and quadratures to move from spectral space where the model is defined to physical space where the data live and where we care about evaluating our covariance function, right? So in this talk, I'll mention how to build these fast transforms or use them if they've already been developed. So in the first part, I'll talk about the setting where you have data, continuous data indexed by some continuous time variable. So our domain is the real line. And in that case, we can use the Fourier transform to map between physical and spectral space. Then in the second part, I'll talk about higher dimensional Euclidean space when you have data on some domain like the plane. And in that case, we'll see that the Bessel function becomes the relevant kernel that we care about. So here, our summations look like the Fourier sums that we had before, but now the complex exponentials are replaced by this Bessel function of order dimension over 2 minus 1. And we'll talk about how to build that fast transform. And then finally, I'll talk about the generalization to manifolds, where now the basis functions we care about are not the complex exponentials or the Bessel functions, but are instead the eigenfunctions of the Laplacian on whatever our manifold M is, right? And so all of these fast transforms can be thought of essentially as trying to speed up matrix vector products with this matrix, this transform matrix phi, whose columns are the basis functions, right? Either complex exponentials or Bessel functions or Laplacian eigenfunctions. So okay, before I introduce our work, I'll give a brief roadmap for sort of existing methods and the type of improvements that we can hope to achieve in these spectral modeling settings by using the fast transforms that I'll discuss in the talk. So for data measured on a grid, like a time series that's measured at regular time intervals, you can just use the fast Fourier transform, the FFT, to move between spectral and physical space, right? And this algorithm is n log n to run. So it's quasi-optimal. And there are therefore a number of popular tools that have been developed over the past 50 years for practitioners to propose a spectral model and work by modeling in the spectral domain, right? So this is now essentially a classical method in applied statistics. However, methods for, say, non-equispaced data in higher dimensions are the focus of more recent work. So this method by Greengard et al. From last year gives a computational method for working with spectral models, which is quasi-linear in the number of observations n, but it requires m to the d Fourier basis functions, right? So we see here that for dimension 2 or 3, you might start to pay a sort of curse dimensionality cost in these settings. So in the first and second part of this talk, we'll think about how we can circumvent this cursive dimensionality for certain models to get to this quasi-optimal m plus n log n time. And then another setting that's seen a lot of recent work is the setting of a two-manifold. So you have data on some surface, like in the engineering application that I mentioned earlier. And in this case, the general computational costs are m times n, where m is, again, the number of basis functions, or the number of columns of my transform matrix, and n is the number of observations. So in the third part of this talk, we'll think about how to move this using a fast transform to m to the 3 halves plus n cost, which can be a drastic reduction depending on how many basis functions you need, right? So this is essentially the roadmap of the talk. So, okay, let's jump in with this first part, where we'll treat these continuous time processes. So going back to our basic idea, the idea is we're given a spectral model S, and then we want to evaluate the covariance function, which we'll call K of Rj, where we have a large number of Rjs, right? And in this case, if we assume our S is real and symmetric about the origin, then this reduces to just a cosine transform. So we'll go about computing this cosine transform by computing panel integrals. So the idea is we'll start at the origin and we'll integrate from 0 to some omega naught and see what the contribution of that integral is, and then pick a new panel, omega naught to omega 1, and compute that panel integral until the contribution of the panel integral is sufficiently small and we've achieved convergence, right? And in this case, the nodes and weights are again given by these omega k and gamma k, right? So this is computationally fast to do because we have the non-uniform fast Fourier transform, or the NUFFT, which is essentially an analog of the fast Fourier transform that uses some analysis-based tricks to allow you to compute Fourier transforms with irregularly spaced data. And again, we need this sort of NUFFT because the distances rj at which we want to evaluate the covariance are in general not going to be equispaced. And the nodes omega k will choose to be a Gauss-Legendre quadrature rule. And so those are also not going to be equispaced. So we need this sort of flexibility to use a non-uniform transform. So the computational advantages that come with this, besides just the speed up, is that by using panel quadratures, we can make this method locally adaptive. So if you have a spectral model S that has some variation in some domain, you don't have to make your quadrature rule globally finer. You can refine only in specific areas, right? And you can also make this very efficient for slowly decaying spectral densities because you only need very few quadrature nodes way out in the tail of that function. So if we put these things together, we can, this sort of local adaptivity and some truncation error analysis, we can accelerate these panel integrals with the NUFFT, and this allows us to evaluate our covariance function K at millions of distances R from our spectral model in a couple seconds on a laptop. So this is very much usable code, and we have a Julia package that implements all of this. So after we put together these pieces, we can essentially walk through the modeling paradigm that we set out at the beginning, which is I propose some spectral model that captures some relevant phenomena in data. So in the first line, we have this oscillatory Matern kernel, which is the popular Matern spectral density, which is this first term multiplied by this 1 minus oscillatory term. And what that oscillation induces in the kernel, which you can see in the first row of plots below, is that the corresponding covariance function has negative correlations at small length scales, which encourages this sort of oscillatory behavior. And if you look in the third column at this sample yx, you see that oscillatory behavior in samples of the process. So if you have if you have data where you think this is a meaningful attribute of the data, then you can write models that actually capture that type of behavior. And the second function we show is this sort of semi-parametric function, where now we parameterize our spectral model in terms of the coefficients of a Chebyshev series, right? So you can make this essentially arbitrarily flexible depending on how many coefficients you retain in this Chebyshev series, right? So if you look at the bottom row of plots, you see the spectral model for some choice of coefficients, and then this covariance function in the center, which if you were to show to me a priori, I would have no idea if that's a positive definite function, but because we've written it in the spectral domain, it's positive definite by construction. So this is the advantage of this type of modeling approach. Okay, so now to further see like when this would be a useful modeling paradigm, let's look at some real data. So here we have vertical wind velocity data at about 1 second time intervals taken by a Doppler LiDAR device. So it's mostly equispaced, but it has some timing irregularities based on instrument delays, and it also has gaps where the instrument has to reset to its original position, right? So we're going to treat this like a process which is indexed in continuous time, right? And we'll consider this so-called singular Matern model, which was proposed by Porco and Stein in 2012, but never actually fit to data because we didn't have this sort of computational machinery in place. And the idea is to just take the Matern model and then add an integrable singularity at the origin in spectral space, right? And the effect of this integrable singularity is now the corresponding covariance function decays very slowly, right? So it decays like r to the negative 1 plus alpha, whereas if we didn't have this singularity, then all the Matern kernels decay exponentially in r, right? So this gives us a model class that allows us to model extremely long-range dependencies in data, right? And because algebraic singularities are straightforward to integrate using panel quadrature, and because this kernel K is not available in a numerically stable closed form, right? It's only available in the spectral domain. This is sort of the perfect opportunity to test our approach and use numerical integration to compute our covariance matrix entries. Right? So let's do that. Let's fit both models to data. So here we're fitting both the traditional Matern without the singularity and the singular Matern model to this LiDAR data using maximum likelihood, right? Where all of the entries of our covariance matrices are calculated using our numerical integration approach. So on the left, we show the spectral models, which are using the fitted parameters. And on the right, we show the corresponding covariance functions, right? So it's obvious from the plot on the right that when you fit this singularity parameter, you introduce this very long range dependence, right? So the correlations are non-zero, even far from the origin, whereas the traditional Matern model immediately decays to zero exponentially, right? So it captures only those correlations very near the origin. So, and also if we look at this little table on the bottom, we show the log likelihood of the original Matern model and the singular Matern model, and we see that we've increased the likelihood by about 50 units by adding only a single parameter, right, which is the singularity. So from a sort of information criteria perspective, this is a sort of significant improvement, right? And if we look at the errors suggested by the Fisher information, we see that this parameter, the singularity parameter, is well resolved. That's the sort of numbers in parentheses at the bottom. So we have high confidence that this is like a meaningful parameter to add to this model that actually helps better model the phenomena in the data. Okay, so this should serve to demonstrate that writing these types of flexible statistical models in the spectral domain can help you better capture scientifically relevant phenomena. Okay, so I'll move on to the second part, unless anyone has questions here. Otherwise, I'm happy to take questions at the end. So, okay, so now let's move on and think about how we can use similar ideas for data in higher dimensions. Okay, so um, we'll note that if your spectral model is not just stationary, but also isotropic, meaning that it depends only on the norm of this vector omega of frequencies in d-dimensional space, then you can actually analytically integrate out all of the angular variables in your Fourier transform to move from a d-dimensional Fourier transform to a single dimensional integral whose kernel is now the Bessel function. And this integral is called a Hankel transform. So essentially, we've circumvented the curse of dimensionality by using the fact that S is really a one-dimensional function, right? It just happens to live in d-dimensional space. So again, this presents a sort of computational challenge because now when we evaluate the integral above, the kernel is no longer the complex exponentials, right? So we can't use the non-uniform fast Fourier transform. We need instead a non-uniform fast Hankel transform, which evaluates these linear combinations of Bessel functions, right? So we now have a different kernel that we need to develop a fast transform for. But if we had this fast transform, then we could use exactly the same adaptive integration machinery that we used in one dimension, right? The only missing ingredient is this transform. So, and I'll note that the fast Hankel transform also appears in applications to imaging, to optics, to astrophysics, electromagnetics. Anytime you have radial symmetry in some geometry, say a lens or a cylindrical waveguide or something like this, the Bessel functions are a sort of natural basis for solving PDEs, for imaging. And so the Hankel transform can become a useful tool. Okay, so how do we develop such a transform, right? So the way we'll do this is by making two sort of basic observations about the Bessel function. So on the left, we have this plot of J0, which is the relevant Bessel function in dimension 2. And we note that if the argument z is small, then the Bessel function is smooth and essentially non-oscillatory. So if we look very close to the origin, we see maybe one or two wiggles, but nothing drastic. And the other observation is that when the argument z is large, the Bessel function is essentially sinusoidal. So if we look towards the right-hand side of that left plot, we see something that looks basically like cosine, right? So the idea is we'll use a local expansion for small arguments, so omega times r less than z, some threshold z, and an asymptotic expansion when the argument is large, greater than this threshold z, right? So on the right, we show a plot of two sort of complementary error expansions where We've picked a particular local and asymptotic expansion so that if we evaluate the Bessel function using either one, then the relative error is small at the beginning for small arguments using the local expansion, and then transfers to being small for the asymptotic expansion if the argument is larger than this crossover point or threshold z, right? So the central idea is to develop these two complementary error expansions. So it turns out that these expansions actually exist in the literature already. So for small arguments omega times r, we can use this low rank expansion, which is due to Wimp from the 60s, which is essentially a closed form representation of the Bessel function near the origin in terms of its Chebyshev series, right? So we're writing down the Chebyshev coefficients in terms of other Bessel functions, right? So the important part is that given a set of frequencies omega k and distances rj, we can apply a block of the matrix that's of size m times n in linear time in n and m, right? It'll cost n plus m times this capital L, which is the number of terms in this low rank expansion, right? And the corresponding asymptotic expansion for large arguments is even more classical. It comes from Hankel in the 1800s, which essentially says that the behavior of the Bessel function looks like a summation of a small number of cosine and sine terms, right? So the important thing to note is that these cosine and sines inside the argument is just omega times r, right? So we can evaluate each one of these cosine and sine terms using the NUFFT in m plus n log n time. And then we just have to multiply by how many terms there are in our expansion, which is m, this capital M, right? So but both of these are a significant speed up over the m times n time that we would see from densely applying the corresponding block, right? And if we perform some error analysis of both of these expansions, then we can pre-compute the number of necessary terms in each one, as well as the crossover point z, where we move from the local expansion to the asymptotic expansion for any user-specified accuracy epsilon, right? So you hand me a tolerance, you say, I want 8 digits of accuracy, and I've pre-computed a table that says, okay, you should use L equals 10 and M equals 3, right? And your crossover point should be at Z equals 10. Okay, so now that we have these two expansions, how do we turn this into a fast transform? So the idea is, given our transform matrix, which we show on the left, some number of the entries there can be well approximated using the local expansion, right? They correspond to small arguments. And some of them can be well approximated using the asymptotic expansion. They correspond to large arguments. So the idea is the line of omega times r equals z, so that's the line at which we cross over from our local to asymptotic regimes. We're just going to recursively partition our matrix along that curve into blocks which are either entirely local or entirely asymptotic. And we'll continue this process until we've squeezed all of the blocks which are neither local nor asymptotic into an order one essentially band so that we can evaluate them directly without impacting the asymptotic cost, right? And then when we want to apply this transform to a vector, we simply apply each block using the corresponding expansion to the vector, right? And this leads to a fully non-uniform quasi-linear time algorithm for applying our transform matrix to any user-specified accuracy, right? And we now have a registered open source Julia package for this. So if you're a Julia user, you could just say add fast Hankel transform and then immediately run whatever order transform you're interested in. Okay, so let's now see how this works in practice relative to computing methods. So again, we'll think about this singular Matern model that we talked about in the one-dimensional case for the LiDAR data. And we'll pick the parameters so that the spectral model is approximately compactly supported on the unit, essentially on the unit disk, right? With the norm of omega between 0 and 1. Right? So then we'll compute our covariance function in two ways. The first way is we'll use the non-uniform fast Hankel transform we've just developed to compute this one-dimensional integral, right? And the second is we will just compute the two-dimensional Fourier integral outright. So we'll use a two-dimensional tensor product quadrature rule on the unit disk, and then we can use the 2D NUFFT to evaluate this, right? So this has the advantage of it's a simpler transform. It's just the Fourier transform instead of the Hankel transform. But of course, it's a two-dimensional integral rather than a one-dimensional integral. So you do have that cursive dimensionality. Okay, so how does this play out in practice? So on the left, we're showing both sets of quadrature nodes, right? So in one dimension, we need only these highlighted purple nodes from 0 to 1. And for the two-dimensional NUFFT, we need all of these two-dimensional nodes on the unit disk, right? So on the right, we show the runtime of both of these algorithms for various choices of the maximum distance that I want to evaluate my covariance function at, right? So if we look, say, on the right at this dark blue line, so this log2 of Rn equals 6. So this is a case where we're evaluating at a very small distance r. So essentially, all of our integrands are only mildly oscillatory. So we see that the dashed line, which represents the 2D NUFFT, is much faster than our Hankel transform, right? And this is because essentially the cursive dimensionality hasn't set in. You don't need that many nodes for this non-oscillatory function in either 1D or 2D, right? But if we look at something like this green line or purple line, we now see we're evaluating the transform at a much larger distance. It's much more oscillatory. And now we see the cursive dimensionality, the fact that we need R square nodes in 2 dimensions and only R nodes in 1 dimension, right? And if we look at even higher distances, so these yellow or blue lines, we see that we can continue to take higher and higher distances with incurring only a linear cost, whereas the two-dimensional problem incurs this quadratic cost. Right? So this is sort of the advantage of using the Hankel transform, is this circumventing of the cursive dimensionality. Okay. So now that we have all of these tools in place, we can do exactly what we did in 1 dimension for these two-dimensional problems, right? We can propose a spectral model, and then we can use our adaptive integration framework to compute any of the covariance values that we need. So that's that middle panel here. And then after having done that, we can do downstream tasks like sampling from our process and things like this, as you see on the right, right? So here's again our oscillatory Matern model written only in the spectral domain, and we numerically compute the relevant covariance functions. So this is the sort of speed up that we talked about in the introduction from this m to the d cost, which you incur in, say, the two-dimensional example we just had, versus this quasi-optimal m plus n log n cost that you get by circumventing this cursive dimensionality and using a Hankel transform instead of a Fourier transform. Okay, great. Any questions about this section before I move on? Give everyone a chance.
I have a question.
Mm-hmm.
This is Grady, right? Sorry, I didn't have my camera on. But the question is about the cost here. Does it depend on new in some way also? I mean, the smaller new is, the larger number of terms you need to sum or something?
Exactly. Yeah, yeah, yeah. And that if we think of M as dimension independent, then that's essentially true, right? Like if you have a very rough random field or you have a very slowly decaying process, then or slowly decaying spectral density, then you'll need M to the D nodes, whereas for the Hankel transform, you'll need M. But exactly what you're saying is correct. Like if you have a rougher spectral model, you'll need more basis functions.
Okay, thanks.
Yep. Okay, great. So, um, okay, so that concludes our look into 2 dimensions where we've built this fast Hankel transform to evaluate these covariance functions. And now we'll move on to the manifold setting, right? So the idea here is essentially what we've talked about in the first two sections. We can note that the complex exponentials, e to the I omega x, that we were working with in 1 dimension, and the Bessel functions under a suitable scaling are exactly the eigenfunctions of the Laplacian on the real line and on essentially isotropic d-dimensional space. So Rd modulo the sphere, right? So for general manifolds, we can imagine a similar transform that maps spectral to physical space, which we'll call the manifold harmonic transform, right? So now the basis functions that we're interested in are these Laplacians, are the eigenfunctions of the Laplacian phi k, right? And again, we can think about this as a matrix vector product whose columns are eigenfunctions of the Laplacian, right? So what do these functions look like in practice? So here we've computed a few of them on this cow mesh. And so we're plotting, we're plotting each one of these functions and giving the index k as well as the corresponding eigenvalue lambda k, right? So you can see that as the eigenvalue increases, we have oscillations on the surface on smaller and smaller spatial scales, right? So in this way, the Laplacian eigenfunctions provide a sort of natural multi-scale basis for functions and operators that live on the surface of M, just like we would see from, say, the Fourier basis, right? So the primary difficulty here is that the eigenfunctions of the Laplacian on a general manifold have to be computed, and we don't have sort of classical analytical expansions that we can use in this case, like we did for the Bessel functions, right? So, sort of lacking these sort of analytical expansions, the only tools we have left are essentially linear algebraic tools. So, in order to motivate the sort of linear algebraic structure that we want to take advantage of for this manifold harmonic transform, we'll revisit perhaps the original fast transform, which is the FFT. So what is the FFT doing? So if we define our nth roots of unity, then the DFT is given precisely by this sum, right? So I want to apply the DFT matrix of size n, which I'll call phi n, to some coefficient vectors c. Then the jth entry of that is simply equal to this sum, right? And what the FFT is doing is dividing this into two separate summations, each of length n over 2, right? Where the second, according to whether or not the coefficient is even or odd, right? So the even coefficients go in the first DFT, and then we add what's called the twiddle function, or the twiddle factor, psi sub n to the j, multiplied by the second DFT for the odd terms, right? And this is what leads to this sort of recursive algorithm for the FFT, right? But we can also view this as simply applying a rank 1 matrix to some permutation of the results from these smaller transforms, right? Where all we're doing is writing this now as in matrix form, right? So as a result of this structure, it turns out that every n over 2 to the L by 2 to the L block of the DFT matrix has exactly rank 1 at all levels from 0 to log 2 of n, right? So under a suitable permutation, this is true. And this is a sort of non-obvious fact. So it shows that all matrices of size n by 1 so those are trivially rank 1, but also the n over 2 by 2 matrices are all rank 1, and the n over 4 by 4 matrices are all rank 1, etc. Right? So these are the blocks that we're showing in this diagram at the bottom. And this is what's known as the complementary low rank structure. So we're moving down a tree in space, so we're subdividing space, while moving up a tree in frequency, so agglomerating two sections of frequency space. And at each level, all of these blocks have low rank, right? In the FFT case, they have exactly rank 1. So we'll try to use a similar complementary low rank structure in the manifold harmonic transform matrix, right? Whose columns are now the Laplacian eigenfunctions instead of the complex exponentials, right? So it turns out that the correct generalization of the algebraic structure of the FFT is called the butterfly factorization, which was introduced originally in the 90s and sort of codified in this paper by O'Neill et al. in 2010, which generalizes this structure from the FFT, whose blocks are exactly rank 1, to operators whose blocks may have low epsilon rank for some tolerance epsilon, right? So we're talking about now about low numerical rank. So the central idea is that for each block at each level, we'll compute a row basis using the row bases from the previous level, right? So let's start at the first level and look at these first two block columns. So let's assume that we have low rank factorizations for those block columns, which we'll call U alpha V alpha star and U beta V beta star, right? So now if we want to compute a low rank approximation for this green block, U tau at the next level, we note that the green block is exactly putting the two original block columns next to each other and taking the top half, which we'll express with this plus operator, right? And if we write out in this sort of second expression, if we write this out as in block matrix form, we see that we can simply take a low rank approximation to this matrix U alpha plus U beta plus, right? And if we take a low rank approximation there, that gives us a basis U tau times R tau star, right? Now we see that R tau exactly maps the row bases at the previous level, V alpha and V beta, to a row basis V tau at the current level, right? So we've taken our row bases that we've already computed at the previous level and we've mapped them up a level to the current block to build a low rank factorization for that block, right? And this so-called transfer matrix R tau is exactly the R by 2R analog of that matrix we saw in the FFT, 1 and the twiddle factor. Right? So if every compressed block has epsilon rank R, then this factorization is R squared times n log n to store and apply, right? Because we need a transfer matrix R tau for every block at every level. There are O of n blocks at each level, and there are log n levels, right? Okay, so then the butterfly factorization proceeds by just repeating this process for every box, right? So now we look at the lower half of that same set of block columns, and then we move through and look at the next set of block columns, mapping the row bases at the previous level up to the row bases at the current level for all levels, right? And at the end, we have a compressed representation of the matrix that consists of just these n log n transfer matrices, right? So we've drastically reduced the size in memory and the cost to apply. Okay, so if we want to use the butterfly factorization for our manifold harmonic transform, then we need those trees on the row and column spaces so that we can perform those complementary low rank actions, right? So remember that our column space is now represented by the eigenvalues of the Laplacian, right? So if we're interested in eigenfunctions that correspond to eigenvalues 0 up to some maximum lambda m, then we can simply build a binary tree on the interval in eigenvalue space from 0 to lambda m, right? So that tree is easy to build. Okay, but the row space is represented by points on our manifold, right? So now we need a tree that represents sort of the intrinsic geometry of our manifold. And that's given by this construction by Berger et al. In 2010 called Fiedler trees. And so the central idea here is we'll take our original mesh and we'll compute the second eigenfunction of, say, the Neumann problem. In this case, it's not the Neumann problem because we have no boundary data, but if we did, we could assign a boundary condition. But the key point is that we're computing the second eigenfunction, right? And by the Courant nodal domain theorem, we know that this eigenfunction consists of exactly one positive and exactly one negative region, right? So if we want to subdivide our mesh, we can simply take the parts of the mesh on which the value of this second eigenfunction is positive and negative and subdivide them into two new meshes, right? So in this case, we're computing the integral of this second eigenfunction phi2 over each patch. And if that integral is positive, it gets assigned to partition 1. And if it's negative, it gets assigned to partition 2, right? And now, of course, we can continue this process and compute new second eigenfunctions on these new submeshes to continue building our tree. So now we have a sort of a tree on the surface of our manifold that respects the intrinsic geometry, right? None of these things reference the fact that we're embedded in 3 space. They only reference the sort of intrinsic geometry of these second eigenfunctions, right? And this gives us a suitable tree to perform all of our butterfly factorizations. Okay, so now that we have all of the tools ready, let's put them together and see how this performs in practice. So here we'll take this deformed torus mesh, and we'll take our points xj that define the rows of our transform matrix to be Chebyshev nodes in a quadrilateral mesh of this geometry. And now we need to compute the eigenfunctions and eigenvalues numerically, and for that we'll use a spectral collocation scheme by Dan Fortunato. And then we'll build a Fiedler tree on the surface of the manifold, as just discussed, and a binary tree on the interval in eigenvalue space that we care about, say lambda or 0 up to some maximum lambda m, right? And then we'll compute our butterfly factorization by computing all of the low rank factorizations up the tree in the way that we discussed 2 slides ago, right? So on the right, we show the results. So here we have the size of the resulting factorization in memory as a function of n, the number of discretization points. And here we take the number of eigenfunctions in our transform matrix to be n over 25, right? So as we get a finer and finer mesh, we can resolve eigenfunctions that have finer and finer oscillations. So we should also be able to take a larger number of eigenfunctions. So this is a sort of natural scaling. It's essentially saying we want to keep the points per wavelength constant, right? So in this setting, if we look at the empirical results, we see that for, say, a 3-digit tolerance, we get almost an order of magnitude speed up at 50,000 points, right? And we note in particular that the asymptotic scaling seems to be something like n to the 3 halves, right? Okay, so I think in interest of time, I'll skip the theoretical analysis, but I'm happy to talk offline with people about can we prove n to the 3 halves? What is the theoretical sort of machinery we need to establish this asymptotic complexity? But instead, I'll move and talk about some applications now that we have all of the sort of components in place. So first, let's talk about our motivating application, which was Gaussian random fields, right? So the this butterfly accelerated manifold harmonic transform helps us to accelerate sampling from Gaussian random fields using this construction by Borovitsky et al., where we use this truncated Karhunen-Loew expansion. So the idea is to say our random field y is equal to a superposition or a linear combination of these eigenfunctions lambda, or sorry, eigenfunctions phi k, with random amplitudes scaled by the spectral density S applied to the corresponding eigenfunction lambda k, right? So if we think about this in matrix vector form, we can draw a sample from the process by simply applying the manifold harmonic transform to a random vector whose entries have variances which are scaled by the corresponding spectral model that we proposed, which is S, right? So what does this look like? So here we have each column represents a different spectral model. So in the first two, we have the Matern model. So this is a sort of very standard form for the spectral density. And we use that to draw samples from this process, where in the first row, we have the deformed torus mesh we were thinking about before. And in the second row, we have a Lake Superior mesh, where now we've enforced a Dirichlet boundary condition, right? So this type of modeling is useful because you can use it for things like fish populations or things where you know that the boundary data should be 0. Or you can also use Neumann boundary conditions or whatever is useful for your particular statistical model. You can sort of bake those into the eigenfunctions, right? And so for both of these, we have about 50,000 degrees of freedom in the mesh, and we compute about 2,000 eigenfunctions, and we see about a factor of 10 compression. So even in these sort of not extremely large settings, we can still see a meaningful speed up. And also, I'll mention that while we use a quadrilateral mesh for the deformed torus, we use actually a triangular mesh and finite elements for the Lake Superior mesh. So this is the manifold harmonic transform is essentially totally agnostic to the discretization you have. Okay, and so this is sort of where we get our improvement from m times n complexity to m to the 3 halves plus n complexity that we talked about in introduction, right? So this is the sort of speed up that you get from applying a fast transform to this problem. Okay, so another application that I think people would be interested in is that you can actually use the exact same framework when you don't even have a mesh and you just have sort of noisy mesh-free data by using this framework called Laplacian eigenmaps, which has been popularized in the past 20 years or so, where we approximate the Laplacian eigenfunctions for data that lie up sort of close to some lower dimensional manifold by using the eigenvectors of the graph Laplacian for some suitable weighting, right? So you take a weighted graph Laplacian using something like the heat kernel here, and that allows you to compute approximate Laplacian eigenfunctions on a noisy sort of mesh-free geometry. And if we repeat the same scaling experiments that we did in the previous section, now we're computing essentially 2% of the spectrum and compressing it, we see that, again, we have approximately n to the 3 halves scaling and about an order of magnitude speed up even at this sort of n equals 50,000 very reasonable size, right? So this sort of indicates that there's some practical value to using this transform, even in settings where you don't have, say, like extremely high quality, high accuracy eigenfunctions. Okay, and the final application that I'll talk about is this paradigm suggested by Vallée and Levy called spectral geometry processing, where you actually use the manifold harmonic transform basis to parameterize and modify the underlying geometry. So the idea here is we'll essentially solve the inverse problem to compute coefficients of each of the three-dimensional mesh vertex coordinates in the Laplacian eigenfunction basis, right? So I take all of the x coordinates of my points in my mesh, and I say, what is the correct coefficients in the eigenfunction basis that returns those x coordinates? I do the same thing for the y and the z coordinates. Now I have a representation in terms of the coefficients in a manifold harmonic series. Now I can multiply by some filter function f, which attenuates or amplifies geometric features on various length scales. And then I can map those modified coefficients back to physical space to give me a new modified mesh. Right? So this allows for fast interactive mesh design and geometry modification. But storing this transform matrix phi was historically prohibitive. And this was what was said in the original paper. So let's try this in practice and see how this looks. So here we have the sort of standard Stanford Dragon mesh, but it's a quadrilateral mesh that consists of about 500,000 tensor product Chebyshev nodes, and will compute about 5,000 eigenfunctions, which is sufficient to recover the mesh. Um, and the dense transform matrix phi takes about 20 gigabytes of RAM, which pushes the limits of the consumer laptop that I'm running all these experiments on. Um, but if we look at the compression sizes, so now if we ask for only a 3-digit accurate transform, we can get that down from 20 gigabytes to only half a gigabyte, so a compression ratio of about 37. And if we want a higher accuracy transform, say 6 digits, we can still easily fit that in our computer with 1.3 gigabytes, so a compression ratio of about 14. So, and here in the figures, we show the recovered coordinates x tilde. So this is essentially solving the inverse problem to compute the coefficients and then mapping those back to physical space. So this should be exactly the original geometry if no error is incurred. And then in the second and third images, we show applying filters to these geometries. So in the middle panel, we have a low pass filter where you essentially cut out all contributions from these high eigenfunctions. So we see that we take away all of the detail from the geometry. And in the last image, we have essentially a band bump filter. So at high frequencies, we accentuate the contribution of those eigenfunctions on those length scales, which corresponds to sort of blowing up and sharpening the features that have sort of sharp corners in this geometry. Right? Okay, so sort of to summarize and bring everything together. So the central idea is that writing Gaussian random field models in the spectral domain is highly flexible and expressive, but it requires fast transforms and quadratures to move from spectral space, where the model is defined, to physical space, where the data live. Right? But by developing new Fourier-like fast transforms using either classical expansions in the case of the Hankel transform or modern linear algebra in the case of the manifold harmonic transform, we can see speedups both for Gaussian random field modeling as well as in other applications where we want to do harmonic analysis for these settings. Yeah, so with that, thanks very much for your attention, and I'm happy to take any questions.
Awesome. Let's thank the speaker by clicking buttons. And I'll stop the recording.